Welcome to Brain Vision.
16.52, so we've got a rope that's under a tension of 200 newtons and it's fixed at both ends. We're told that it's oscillating in its second harmonic pattern for the standing wave. Now we're given the function for the displacement, and we'd like to find out some things about this rope. Like we want to find its length, the wave speed, the mass of the rope, and then what the period is of the third harmonic standing wave pattern. So first, for the second harmonic, we know that we're going to fit two half wavelengths in, because for a string that's fixed at both ends, the number of the harmonic is the number of half wavelengths. So the wavelength is just going to be the overall length of the rope. The frequency, as we know, is the speed divided by the length. It's the speed divided by the wavelength, but in this case it's just the length of the rope. So here we can see that the wave number is pi over 2 radians per meter. We know the wave number is also equal to 2 pi divided by the wavelength. And we know that the wavelength is the length of the rope. So then just rearranging this for L, we find that the length of the rope is 4 meters. Now we know omega from this is 12 pi radians per second. Which is also 2 pi f. We could in fact just divide the you know what, actually let's just think of it that way. It's easier. So the omega is 12 pi radians per second, and the wave speed is the angular frequency divided by the wave number. We've just found both of these things. The wave number is pi over 2 radians per meter. The angular frequency is 12 pi radians per second. And so we get 24 meters per second, because the pi's cancel, and then 12 divided by 1/2 is 24. So now we want to find the speed. We know on a string that that's equal to the square root of tension divided by the mass density. So this looks promising. We have the mass density, and we know that that's equal to the mass divided by the length. And so right here is the mass, which we want. So then the mass is going to be the tension times the length divided by the speed squared. Conveniently found out the length and the speed, and we're told the tension. And so we get that the mass is 1.4 kilograms. So for the frequency of the third harmonic, we know it's going to be 3 times the speed divided by 2 times the length, because it's NV over 2L, so N equals 3, put that in there, that's what we get. We know that the period, of course, is just the inverse of the frequency. So 2L over 3v. And so we end up with 1/9 of a second, 0.11 seconds.